you see the name Gromov. Perhaps you know that Mikhail Gromov is a Russian mathematician who got the Adler Prize this year for his contributions to differential geometry. And one of his contributions are so-called Hausdorff-Gromov limits. And you will show how it is related to quantum field theory. Please.
Thank you. Thank you very much. Okay, first of all, let me thank the organizers of this conference to give me the opportunity to talk here. And also because, I mean, the invitation to talk here was a good motivation to try to finish this work in time. So it's, as you see, it's a joint work with Henning Bosselmann and Luca Suriano. My point is try to describe the relation between quantum Gromov-Hausdorff limits and scaling limits in quantum field theory. More precisely, to give to the scaling limits of Buchholz-Verch a more mathematical description in terms of limits in a suitable metric space. This was exactly the point of Riffel when he introduced the so-called quantum Gromov-Hausdorff metric, tried to describe the distance between two spaces, for example, to sister algebras, and to study convergence with respect to this metric. So let me first introduce what the quantum metric space and the corresponding quantum Gromov-Hausdorff distance is according to Mark Riffel. This is a short bibliography. There are some papers by Mark Riffel where he introduced all these notions, and then some papers by David Kerr and Hanfeng Li, two former students of Riffel. David Kerr introduced the so-called matricial quantum Gromov-Hausdorff distance, and Hanfeng Li studied in particular the consequences of that for sister algebras. There is also a paper of me in collaboration with Tommaso Isola, in which we also studied some connections of this metric with the problem of completeness for sister algebras. Originally, the notion of Mark Riffel referred to order unit spaces. According to basic results of Kedison, an order unit space is the same as a space of affine real-valued functions on a compact convex set. The order structure is then simply the pointwise order of functions. The norm is the usual subnorm, and the unit is simply the constant function equal to 1. Then a Lipp seminorm on such an order unit space X is a densely defined seminorm with these two properties. First, that L vanishes only on the multiples of the identity. And second, that if you take the elements with norm, with bounded norm and bounded Lipp norm, you get something which is norm compact. Such an object was called quantum metric space by Mark Riffel. And an important observation is that the Lipp seminorm induces a distance on the states. So you simply define the distance between two states as the supremum of the difference on an element X, and the supremum being taken over all elements of norm less than 1. Okay. Of course, there are always errors in the slides. This is not the norm. This should be the Lipp seminorm. In this way, dl is a distance which induces the W star topology on all bounded sets, so in particular on the states of this order unit space. Of course, this is a non-commutative version of what you expect on functions on spaces. So the Lipp norm is the usual Lipschitz norm on functions, and the corresponding distance is simply the what you get when you pass from distances, from a distance between points to distances between measures, in this case states. Using this notion, Riefel defined a distance between order unit spaces. So once you have a pair of quantum metric spaces, so order unit spaces with Lip norms, you consider the family of all Lip norms on the direct sum, which induce respectively the Lip norm Lx on x and Ly on y, and define the quantum Gromov-Hausdorff distance between x and y as the infimum over all these Lip norms of the Hausdorff distance of the states over x and the states over y embedded in the states over S direct sum of y. So it is essentially the same as taking the Gromov-Hausdorff distance between S of x and S of y, but instead of taking all possible metric embeddings, you only take those embeddings in which the distance comes from a Lip seminorm. This implies that once you have distance 0, then this is actually an isomorphism between the corresponding order unit spaces. So in particular, the isometry becomes linear. So this is the theorem of Riefel that this is first of all a distance on order unit spaces, and also it is a complete distance. So whenever you get a Cauchy sequence of order unit spaces, it's convergent to an order unit space. Okay, then the second step is to pass from order unit spaces to sister algebras. Of course, the self-adjoint part of a sister algebra is in a simple way an order unit space. You have an order, a unit, and a norm. But if two sister algebras are isomorphic as order unit spaces, this doesn't mean in general that they are isomorphic as sister algebras. So one should modify a bit the distance in order to get a distance between sister algebras. This was mainly due to David Kerr. For sister algebras, it's enough to consider only 2 by 2 matrices. So the D2 quantum Gromov-Hausdorff distance between A and B will be defined as the infimum over Lip seminorms of the Hausdorff distance between the 2 states over A and the 2 states over there should be a B, of course, in the second point. Well, by S2 of A, I mean the unital completely positive maps from A to the 2 by 2 matrices over C. And the distance on 2 such unitary completely positive maps is defined as here. The one misprint is that the second A should be a B, of course. Is this? Yes. I'm sorry? Yes, that's right. That's right. Thank you. It's already the same mistake in the previous slide, but okay. So the theorem of Kerr is that this D2 quantum Gromov-Hausdorff is indeed a distance on the space of Lip sister algebras modulo isomorphisms. So this is a way to modify the quantum Gromov-Hausdorff in order to get the distance between sister algebras. Let me note that this distance is not complete on sister algebras. So in general, it is not true that if you have a sequence, Cauchy sequence of sister algebras, you get a limit as a sister algebra. And essentially, this is due to the fact that the Lip norm is not multiplicative in a sense. So that if you have a bound on L of x and L of y, this does not give any bound on L of xy. However, if you assume so-called Leibniz properties on L, so that L of AB is lower or equal than the norm of A times L of B plus L of A times the norm of B, then a Cauchy sequence of Lip norm sister algebras with such a property is converging to a sister algebra. So if you recover, in a sense, some kind of multiplicativity, then you get that the limit is a sister algebra. And this property, Leibniz property, is, for example, satisfied whenever the Lip norm is simply the norm of the commutator with a given operator, for example, the Kohn-Dirac operator in non-commutative geometry. In general, one can extend these notions to operator systems, replace the distance with a complete distance, and then you get a complete space. So in general, a Cauchy distance, a Cauchy sequence will converge to an operator system, not necessarily to a sister algebra. Only if you add some kind of property like the one mentioned before, you get that the limit is indeed a sister algebra. Okay, so this is the setting of Riffel, Kerr, Lie, etc. on convergence of Lip norm sister algebras. Now let me see if one can do something in quantum field theory. In particular, let me mention the typical properties of compactness. As you see, compactness plays a main role in Riffel distance. So the properties of compactness are usually expressed in terms of nuclearity of maps. These are some references. Of course, there are very many references about that, but the starting paper by Haag and Zwieka, and then this unpublished note by Frederik and Hertel, which then was finally written and developed by Buchholz and Portman, and the paper by Buchholz and Wickman, and then a paper by Buchholz and Antoni Longo on nuclear, on modular nuclearity. So generally, the compactness property for local algebras has this form. You have a map from a local algebra R of O to some target space, Banach space P, and you ask that such a map is compact or nuclear. I will use in particular the Buchholz-Portman nuclearity in the following. So in this case, this map is a dual of a suitable map T star, which is a map from the produal of V of H to the produal of the von Neumann algebra of O with dense range, which is given by such a formula. You take a normal state on V of H, you multiply left and right by e to the minus h, generally e to the minus beta h, but I mean I simply put beta equal to 1 in this case, and you restrict to the algebra of O. So once you have such a nuclear map, in particular, you can get a sort of Lip norm on the range of the produal of T, which is defined as in this way, and using this Lip norm, of course, you get that the produal over O is norm with elements with Lip norm less than or equal than 1 is norm compact, and you get a dual Lip norm on the von Neumann algebra, which is expressed exactly as the dual of the Lip norm on states, in such a way that then the unit ball is compact in this L prime, and in particular the topology induced by this norm on the bounded sets is simply the weak star topology of the duality between the von Neumann algebra and its produal. Okay, let me just note that instead of having semi-norms in this case, we have norms. This is essentially due to the fact that the starting space is not an order unit space here, but a state space. So there is no unity, so there is no need to have annihilation of multiples of the unity. But the main point is that the framework we get is in a sense opposite to that of Riffel. So the Riffel setting is that the duality is between a sister algebra and its state space, and the Lip norm is in the sister algebra, a dual Lip norm is in the state space, while in quantum field theory you have an opposite situation. You have the duality between a produal of a von Neumann algebra and the von Neumann algebra. The Lip norm is on the states, and the dual Lip norm is on the von Neumann algebra. So we cannot actually use the Riffel construction, but we have to modify it to adapt to the situation which we have in quantum field theory. So this is the definition that we gave. A Lip von Neumann algebra, ML prime, this prime is simply to recall that it is not a Lip norm but a dual Lip norm, has this dual Lip norm, which is a star invariant norm, which induces the W star topology, so the weak star topology, on the bounded subset of N, or equivalently, the predual as a densely defined norm, such that the elements of Lip norm less than 1 is norm compact. Once we have this notion of Lip von Neumann algebras, one can try to define a distance exactly as Riffel did, but with ideas of curves, so passing to matricial to a matricial distance. So first of all, one extends L prime to the 2 by 2 matrices over M. It is not very important how to extend it. For example, one may take simply the maximum of the Lip norms of the entries. And then, for a pair of Lip von Neumann algebras, one considers the set of all dual Lip norms on the direct sum, which restrict to L prime 1, L prime 2 on M1, M2, and then define the corresponding quantum Gromov-Hausdorff distance as the infimum over all these dual Lip norms L tilde of the Hausdorff distance between the positive part of the unit bolts of the matrices over M1, respectively, of M2. Okay, there is also, yes, there should be a 2 here. Okay. This is the notion of distance that one can produce, and the point is that this is indeed a distance. So the starting point is that this is the distance on the space of Lip von Neumann algebras modulo isomorphism. So if two von Neumann algebras with dual Lip norms have 0 distance, they are actually isomorphic as von Neumann algebras. This is, in a sense, the non-trivial property to show that distance 0 actually imply isomorphism. As in the case of sister algebras, it is probably not true, even though we did not found counterexamples yet, that this distance is complete. Essentially because, again, as above, we do not have an estimate for L prime of the product. Also in this case, it is probably possible to extend this theory to dual operator systems to get a distance, to get completeness, etc. But this we did not do up to now. Then I introduced the next topic, so the question of ultraproducts, because ultraproducts will be the bridge between quantum Gromov-Hausdorff limits and Buchholz-Verch scaling limits. So, okay, these are just very few references. I mean, the first reference concerned ultraproducts on Banach spaces. The second is chapter 5 of a book of Adrian Ocneanu, in which he defined some notions of ultraproducts for Neumann algebras. Even though we do not use his definition of ultraproduct for Neumann algebra, indeed there are some ideas that we borrowed from that paper. And then again the paper with Isola, in which we already showed a relation between ultraproducts and quantum Gromov limits in the case of the Riffel notion. So what is an ultraproduct? You take a family, let's say a sequence, Mn, L prime n of Lip von Neumann algebras with corresponding produals, and an ultrafilter. Then consider first the spatial infinity of n predual, so the sequences which are bounded in norm, uniformly bounded in norm. And then sort of restricted L infinity, so in which we ask that also the Lip norm is uniformly bounded. And then you take the norm closure as a subspace of the previous one. Third, you consider a Banach subspace, K of U, which is simply the sequences of omega n whose limit with respect to the ultrafilter of the norm is equal to 0. And finally, you consider the quotient projection with respect to this Ku. Then this final object, L infinity of Mn star over modulo Ku, is the usual, what is called the ultraproduct of Banach spaces. But here we consider a smaller object, what we call the restricted ultraproduct. So instead of taking the projection of all L infinity of Mn star, we consider only the image of the restricted part. So the part in which you also have the supremum over the Lip norm to be uniformly bounded. This in general is a Banach space and is what we call restricted ultraproduct. Then you may do a sort of dual construction on the dual space. So again, you consider the space L infinity of Mn of uniformly bounded sequences. In this case, one takes no restriction on the dual Lip norm, also because the dual Lip norm is weaker, so of course there is no need to take any restriction. But then, as a subspace with respect to which one takes the quotient, one takes the elements for which the limit of the dual Lip norm is 0. So of course this is bigger than the space of the elements whose norm goes to 0 with respect to the ultrafilter. And then you take the following quotient projection, and again one defined mu as the image under this projection of the space L infinity of Mn. So this is what we call dual restricted ultraproduct. Let me note that this K prime is not an ideal, so in general you should not expect that this quotient is an algebra. Now this theorem gives the first relation between the quantum Gromov-Hausdorff limit and the ultraproduct construction. So suppose that you have a sequence of Lip von Neumann algebras which is convergent to a von Neumann algebra, to a Lip von Neumann algebra in the quantum Gromov-Hausdorff sense, then actually this limit is the same as the dual restricted ultraproduct mu for any ultrafilter. So whenever a limit exists as a von Neumann algebra, any ultrafilter will produce it. The second result is a sort of a converse. First of all, let me say that the family of Lip von Neumann algebras is uniform if it possesses two properties. So the first is uniform compactness, so that the family of unit balls with respect to the dual Lip norms is uniformly totally bounded. This notion would be enough to guarantee a sort of precompactness in the case of Banach spaces, but since we have von Neumann algebras, we need a further condition, which is this uniform normalizer condition. So this is the part, in a sense, which was borrowed by Ocneanu. So once you have, you should take a quotient with something which is not an ideal. What can you do? Well, you simply restrict the original space and take the normalizer of this ideal. So of course the quotient is then necessarily an algebra. So okay, I need some further steps to arrive to the conclusion, but of course you see that this uniform normalizer condition is related to this norm n of a, which is a sort of multiplicative normalizer norm with respect to the L prime. And what is this condition? Is the fact that we can approximate elements in the unit ball with elements still in the unit ball, but with this n norm which is finite. And what kind of approximation do we need? Let me recall you that L prime induces the W star topology, the weak star topology. So this means that A and B are closed in the weak star topology. So we have a uniform density, in a sense, uniform with respect to the with respect to this norm. Okay, and then the theorem is the following. Once you have a uniform sequence of Lippo-Neumann algebras, then this is quantum Gromov-Hausdorff precompact. So such a sequence as a subsequence which is converging to a von Neumann algebra. And so in particular, if you pick any ultrafilter, then the ultraproduct, mu, coincides with the quantum Gromov-Hausdorff limits along the ultrafilter U, and this is of course a Lippo von Neumann algebra. So in a sense, quantum Gromov-Hausdorff limits and ultraproducts are the same under this kind of uniform condition. Okay, so these are just some properties of this norm n, which can explain why it was useful. So the fact that in general it's infinite, but first of all, the elements with finite norm, with finite n norm, form an algebra because of these two properties. And also there is this property, so you can now estimate the L prime of AB in terms of LB and NA. So in terms of n, you get some estimates of the L prime of a product. So why you get, in this case, under this hypothesis, a von Neumann algebra? Well, first of all, you may consider the space A, underline A, of elements which are bounded not only in norm, but also uniformly bounded in this n norm. Then, exactly because this is simply the normalizer, the quotient, so the image under the quotient projection is then a sister algebra. And if you have this uniform property, it means that this sister algebra is then weakly dense in a von Neumann algebra. And this von Neumann algebra turns out to be simply the weak closure of this direct sum representation of A, where the direct sum is over all the states of A which are represented by sequences omega n of normal states for which you have this uniform L norm estimate. So you actually prove that the limit is a von Neumann algebra, showing that it is a weak closure of a suitable sister algebra which is obtained in this way. Okay. Now, great. I'm exceptionally. Now the final part on scaling limits. Okay, these are just few references. Of course, the first two papers by Buchholz-Verch, in which this notion was introduced, and the recent paper by Bostelmann and Antonio Marcella on further notions on that. And okay, so let me consider now the kind of assumptions that we will use in the following. So now O in RO will be a local net of von Neumann algebras in the vacuum representation. H will be the generator of the time translation, so the energy. And an assumption we will consider is uniform nuclearity, so that you have nuclearity of these maps uniformly in R over beta, where beta is the coefficient of H and R is the size of the region. Nuclearity was proved by, of this map was proved by Buchholz and Portman, And we proved that indeed also this uniform nuclearity holds for the real scalar field of mass m in at least 3 special dimensions. So this is the, let's say, uniform Buchholz-Portman nuclearity. Then let me consider another kind of assumption. So in a sense, it's very similar to the previous one, but I replaced the exponential decay with a simple inverse power decay. So 1 plus lambda h to the minus 1 a, 1 plus lambda h to the minus 1. The request also in this case will be of uniform compactness. So instead of nuclearity, uniform compactness. Well, actually, at the first sight, one could say, why should this assumption be satisfied? One only consider exponential decay in order to get some kind of compactness. But indeed, this is satisfied, at least in the sense that uniform nuclearity implies uniform compactness. So that whenever you have uniform nuclearity, so in the sense here, you get uniform compactness for any function of the energy with decays with any kind of decay. I mean, even inverse logarithmic. I mean, there is no importance on the rapidity of the decay. I mean, this is actually the proof of this result is, in a sense, is very simple, and indeed it was essentially given by Buchholz and Portman when they proved that uniform nuclearity implies for some beta implies compactness for any beta. They use an argument which immediately extends to the fact that you can take any decay of in the energy. So, okay, I hope I convinced you that this assumption is reasonable, at least as soon as it is reasonable, the assumption of uniform nuclearity. And then, as a result, one gets that if the net O in R of O satisfies uniform compactness, then one may set L prime of lambda of A as in this formula, and you get a Lippe von Neumann algebra. So the compactness is exactly the one needed to say that it is a dual Lippe norm. As you remember, in the construction of the limit, one uses also a further norm, this normalizer norm, and a simple calculation shows that this norm is indeed equivalent to this other norm. So, and lambda of A bounded means exactly that norm of A plus lambda, norm of the commutator with the energy is bounded. Okay, there is another assumption. Actually, let me just explain what does assumption means. So, when you say that a theory is inner regular, you usually mean that if you take a family of regions which increases to a bigger region, then the corresponding union of von Neumann algebras is dense in any suitable weak topology in the von Neumann algebra of the big region. Here I say essentially the same, but first of all, I consider the weak star topology as the topology which is metrized by L prime, because I mean the fact that L prime is a dual Lippe norm implies that L prime metrizes the weak star topology. And second, I need that this kind of inner regularity is uniform, meaning that only depends on this parameter R, so that I rescale the algebra with O lambda multiplying lambda by R, and the estimate should be uniform in R. Okay. Then the theorem. if one has a net O in R of O, which is local, and satisfies uniform compactness, so the compactness with respect to the multiplication left and right with 1 plus lambda h to the minus 1, and this uniform inner regularity which I mentioned here, then the family lambda O in R of lambda O is a uniform family of Lie von Neumann algebras, which means that any ultrafilter gives rise to a limit. So one can define Rho of U with respect to the ultrafilter U as the quantum Gromov-Hausdorff limit along the ultrafilter of R of lambda O. When lambda goes to 0, the ultrafilter will be an ultrafilter looking at lambda going to 0. These R over U form a local net, which we call then the quantum Gromov-Hausdorff scaling limit. So I simply take the limit in the quantum Gromov-Hausdorff sense for Lie von Neumann algebras of the family of contracting regions. Of course, it's nice that we have a limit, but one should show if there is some relation of this notion with the Buchholz-Verch notion. So the first part actually works quite well. So if you remember the von Neumann algebra, the quantum Gromov-Hausdorff limit von Neumann algebra was given as a suitable weak closure of a sister algebra. The sister algebra was defined in this way. So the elements in L infinity of R of lambda O, where the supremum of n lambda of A lambda is less than infinity, and then norm closed. But since this norm is simply equivalent to norm of A plus lambda, the norm of the commutator, it is the same as taking the sequences in which the supremum is bounded, and then the norm closure. And then a simple computation shows that taking the norm closure here is exactly the same as taking the sequences in L infinity for which this supremum goes to 0 and t goes to 0. So the elements for which the time translations are uniformly continuous. This is the meaning of this property. So the quantum Gromov-Hausdorff von Neumann algebra is simply the weak closure of this of a suitable quotient of this sister algebra. And one can easily compare this with the Buchholz-Verch scaling algebra. This was defined in a way which is exactly analogous. So you take sequences which are uniformly bounded in norm, and you take the same kind of uniform limit, but here, instead of taking only time translations, you should take any space-time translation. But clearly, if the time translation is uniformly continuous by spectrum condition, one gets also this condition. So the two sister algebras indeed coincide. So that first of all, we can reconstruct the Buchholz-Verch scaling algebra using our notions. The second point is, of course, to compare the representations. Well, these are different, as you will see, but maybe not too much different. So the quantum Gromov-Hausdorff representation of this sister algebra, let's say the one associated to one region, is simply the direct sum over all these representations with respect to states which are given by sequences in which you have this uniform boundedness of omega lambda. While Buchholz and Verch consider sort of a vacuum representation, well, actually it's a vacuum representation. So instead of taking this direct sum, they simply take one GNS representation and as a state, they consider a state which can be written in this way, so the limit over an ultrafilter to mean any limit of a state which is obtained in this way. So you take a state omega on the local algebra, you apply to the lambda element in the family A lambda, and then you take the limit over lambda going to 0. Well, okay, of course, with the assumptions above, any scaling limit in the sense of Buchholz-Verch of the original theory embeds as a sub-representation of in the quantum Gromov-Hausdorff scaling limit for a suitable ultrafilter, of course. Maybe one can say something more, but as I mentioned at the beginning, this is still a work in progress, so we should still understand if this for Neumann algebra is actually the same or not. Okay, I think with some anticipation I'm very close to the end. I simply want to make 3 points in the outlook. So, okay, of course, the first point would be that we need to do is to clarify the relations between the two representations, the one considered by Buchholz-Verch and the one considered according to the quantum Gromov-Hausdorff scaling algebra. Let me say that, of course, for the quantum Gromov-Hausdorff limit, we need to take this kind of representation, because this is the only kind of representation which implies that you have actually a limit in the sense of a distance. So it is this for Neumann algebra which is the limit of the sequence which I considered before. And also in general, this kind of prescription, so to take only the states which are in a sense constant along lambda for a general quantum Gromov-Hausdorff limit is meaningless. On the other hand, if you actually consider only scaling limits, so dilations of a given theory, then of course the idea of a constant state is natural. So I mean, also in the abstract setting or in the quantum Gromov-Hausdorff setting, one may always consider, in the case of scaling limits, this kind of sub-representation. And so the question of the relation between these two representations is meaningful also in the abstract setting of quantum Gromov-Hausdorff limits. Well, okay, the second point, of course, I hope, and this is one of the reasons why we tried, to study this question, is that quantum Gromov-Hausdorff limits may help to prove some structural properties of scaling limits. But of course, we did not even start that. And also, I think that this is also an important issue. I think that this kind of limits of Lipf von Neumann algebras can be used in different contexts, still related, of course, to quantum field theory, so using the kind of compactness that one can expect in the setting of quantum field theory. Okay, I'm finished.
Thank you very much for this interesting lecture. Are there questions or comments, please?
I would like to ask you a question about your starting point, what this definition of distances between sister algebras. You started describing the distance between the state space as compact space. You said that's not enough. But what about if you equip the state space with the additional structure of Alfsen, Schulz, and Olsen as a bundle with the orientation or whatever? Can you cook up some distance to take in account of that structure, and then it becomes an appropriate distance of the
well, okay, I don't know. Of course, it is a natural idea. I agree with you. And so probably it is possible, but I mean, to make a distance is not very easy, you know. So in a sense, I think that certainly the idea of Riffel and Kerr is the most economic. I mean, they simply take the distance between metric spaces, and then they show that indeed it implies equivalence of sister algebras. I mean, isomorphism of sister algebras. But of course, other ways are certainly possible, and I think it's an interesting question. I mean.
Next one.
Somehow related to the previous question, can you apply, for instance, this Hausdorff-Gromov distance function to classification of factors? Could you, for instance, take 2-1 factors and try to relate the hyperfinite one with others bigger ones?
Please, could you repeat the question?
Yes, okay. So the question was, is there any way to consider this notion of distance between von Neumann algebras and the question of classification of factors? So is there any distance between, I don't know, type 1, type 2, type 3, something like that? Or
even within type 2-1?
Even between, yes. So, okay, the first problem is that these are distances on von Neumann algebras with a dual Lip norm. This is a crucial point. And so you may have two equal von Neumann algebras with different dual Lip norms, and their distance is not 0. So it's a further structure that, I mean, I don't see any way to associate to a general von Neumann algebra a canonical dual Lip norm in order to follow your suggestion. Maybe, of course, it's possible, but presently I do not see it. I mean, it's.
So, no further questions. So then I would like to thank you again.